Okay, so welcome everyone to the informal seminar for this week. We're incredibly excited and pleased to have Prashant Kocherlakota here from the Black Hole Initiative. So Prashant received his PhD from the Tata Institute of Fundamental Research in Mumbai, and then had a postdoctoral position at the Institute for Theoretical Physics at Goethe in Frankfurt before coming to the BHI at Harvard. Prashant is an expert in kind of tests of classical gravity, and recently he's done a lot in terms of taking experiments like the EHT and asking questions like what can we learn about how consistent classical gravity is with observations. But he has a whole bunch of other interests as well. He will tell you about some of what he does now. So please.
Thanks, Gary. Thanks you all for coming, and also the organizers for inviting me here. So as George mentioned, I'm mostly a theorist, and I'm interested in experimental tests of gravity with black hole images. So that will be the first theme of my talk. And since these event horizon telescope images of black holes are actually looking at black holes that are undergoing hot accretion, I will tell you a little bit also about accretion in black hole spacetimes, both Kerr black holes as well as non-Kerr black holes. So I'll try to give you the main highlights of some recent set of papers. So please stop me if you need any further details at any point. It should be. Okay. So of course, all of this, the impetus has come from this last decade of beautiful set of black hole observations. So on the top here is the paper announcing the first gravitational wave detection, and on the bottom from GW 150914, and this is a binary black hole merger. And the bottom here is the first paper that announces the horizon scale image of a supermassive black hole. So one of the first things that both papers do is to assure us that these observations are completely consistent with general relativity. This is of course of fundamental importance, because we use GR to sort of understand varied astrophysical as well as physical phenomena. And the next thing that they do is also tell us that we can use these observations to sort of understand various aspects of classical gravity with experiment. So this is quite prescient already at this point, and this is the spirit in which we are conducting this line of inquiry. But of course, let me step back for a second and say that the history of experimental gravity is quite rich. It has a long-standing tradition. There's a parameter space which, with the gravitational potential, mass over characteristic radius, and the characteristic curvature, m over here's the Kretschmann scalar, goes as m squared over r6. So we can just plot all the different observational measurements that we've taken on this plot, and the tests of gravity that we've conducted with these guys. So you can see they occupy different parts of the parameter space. And in particular, here are the gravitational wave tests, and here is what the EHT is able to do. So before I sort of briefly touch on what we already know with EHT, let me say that let me highlight two differences. One is that the gravitational waves are coming from mergers of stellar mass compact objects, whereas the images are of supermassive black holes. So these objects are orders like 5 to 7 orders of magnitude difference in size. And also, the sort of context of these tests are quite different. The context of these observations is quite different. So the gravitational waves are emitted in space-time that's highly dynamical. The black holes are merging, highly dynamical space-time, and you're getting gravitational waves off of it. In the second case, for Sagittarius A or M87, when you take their images, the black hole spacetime itself is approximately it's essentially time independent. It's a stationary spacetime. So what this means is that with gravitational waves, we're testing or understanding aspects of the dynamical parts of the theory as well as the radiative parts of the theory. And with the images, you're actually looking at the phase space of stationary solutions of the classical theory. And one of the most famous solutions, of course, stationary solutions of GR is the Kerr metric. This describes a stationary vacuum solution in general relativity. And this has this very nice, beautiful looking metric. We read it off from here. And the metric depends on two metric functions that are dependent on R, and two that depend also on theta. I'm introducing this for notation, but we will come back to this when we generalize to other spacetimes later. Okay, so for this particular metric, everything just depends on the mass of the ADM mass of the black hole spacetime, as well as the spin parameter, A. And I mentioned that these are vacuum solutions. So if you write down the Einstein equations, where this capital G is the Einstein tensor, measuring aspects of the curvature, depending only on the metric, then you can, it's equal to the stress tensor, which describes the properties of the matter in the spacetime. So if I take this metric for Kerr and plug it into the left-hand side here, it will vanish, telling us that it's a vacuum spacetime. Okay, so this is also extremely important because it's a vacuum solution and it also describes black holes in general relativity when this spin parameter is less than the mass. The zero spin limit in particular is called the Schwarzschild black hole. One last thing I want to say on Kerr black holes, although this audience definitely doesn't need all this, is this is a picture of the theoretical picture of a Kerr black hole. This is a slice through the meridional plane. The orange, the yellow lines, the solid and the dashed, describe the ergo surfaces of the spacetime. The orange lines describe the horizon of the spacetime. And here in the center is an equatorial ring, which is the ring singularity of the spacetime. So the curvature diverges at that point. And you can see from these expressions here that everything just depends on the mass and the spin. So this metric is very special. There is no other thing that you need. Give me a mass, give me a spin. I can tell you everything about the spacetime. This is quite nice. And this leads to the statement that Kerr black holes have no other head. And in particular, the expectation that all black holes in nature are also don't have any other head. Okay, so and to be a little precise. So when we are testing GR, when we say we're testing GR in the context of the Event Horizon Telescope, what we're doing is actually testing the Kerr black hole metric, and not actually other aspects of GR, like whether how it radiates gravitational waves, etc. Okay, so Kerr black holes are some of the ones the Kerr black holes are the ones that we love and cherish, but they have some problematic. They have some issues. In particular, they have problematic interiors. They have a spacetime singularity, as we just saw. Furthermore, the singularity can send photons or signals all the way to observers all the way present inside the inner horizon. And even worse, the inner horizon itself is unstable through mass inflation, instability, etc. So the Kerr metric may well describe the exterior geometry, but not it's likely not going to describe very well the interior geometry of astrophysical black holes as well. Also, the space-time between the two horizons is not even stationary. And it's weird to just think that, the interior of M87 has a collapsing cosmology inside it. But that's not a problem. That's just a feature of our realm. Okay. So as soon as we try to think about solving some of these issues, even phenomenologically. So let's say there have been many black hole models that have been proposed that just add some matter at the center of the black hole, which typically violates some energy conditions. And they get rid of the space-time singularity, just to understand what are the effects that you can have on the exterior, like at the exterior. What are the things that you can see?
So if you any weird material or normal material.
So this is material that could be a fluid, but it would violate like a perfect fluid, but it would violate some energy conditions, classical energy conditions. So for example, there is a metric by Sean Hayward, which violates the energy conditions, but he has a way to describe it as some sort of effective vacuum expectation value that you can get some energy density coming from those sorts of arguments, Casimir energy kind of arguments. So classical energy conditions are violated. Whether it makes sense when you include quantum effects is something that's still matter of you have to think about it. Okay, so if when you consider these phenomenological models that differ in their metric from the Kerr metric, so you modify this piece, immediately this guy is going to be non-zero, and therefore you must have some matter typically. So non-Kerr black holes are typically also going to be non-empty. Additionally, there are some black hole models that have been proposed that do away with the inner horizon, and therefore the instability associated. Actually, I should be a bit more precise. So the inner horizon creates instabilities because the surface gravity of the inner horizon causes a mass inflation instability. So models have been proposed where you have a zero horizon, zero surface gravity horizon at the at the location of the inner horizon. This sort of is a way to get around the mass inflation instability that you could get. And here also with regular black hole spacetimes. So there are models that people have sort of constructed to get rid of some of the issues that you can that you face with the Kerr metric. And also what we want eventually is something that has both of these features, ideally, which doesn't have a singularity, which doesn't have these problems of the inner horizon. And the goal with the EHT is to say, okay, if such a guy exists, can we actually tell the difference between this guy and a Kerr black hole from actually looking at their images?
Now, black holes are no longer without air because you are including matter.
Yeah. So the game would then be to detect whether you can set constraints on the hair itself. That'll tell you that it's Kerr or not Kerr. So far, what we found is that it's all consistent with Kerr, and you can set some constraints on the charges, that the hair that you get. Right? But the spirit is, you want to see if there's hair, and can you actually tell that there is hair, things like this. Okay, and also, of course, finally, I should say that these singularities, they occur in general relativity because of these fundamental singularity theorems by Hawking and Penrose. So these must form generically singularities in this theory. So if you actually wanted to get rid of singularities, maybe you might have to modify the field equations as well. So presumably the Einstein tensor changes a little bit close to the center, close to the high curvature regions near singularities. So, and there are a bunch of theories important theories that sort of make changes to general relativity, well motivated. And so you can ask whether if I pick a black hole from one of these theories, how would its image look like? Could I tell the difference from a Kerr black hole? So these are two broad ideas that we're going to go after. And another thing that you can do is to sort of say that this is what you can also do is to say that it must be a Kerr black hole, but how Kerr is it? How can we set constraints on the sorts of deviations it can have from Kerr? If we set constraints on those deviations, then we know it must be a Kerr black hole. So it's sort of that logic. And you can invent parameterized metrics that tune away from Kerr, set constraints on those parameters, and then build confidence in the fact that it's a Kerr black hole. So there are two interrelated themes for doing tests of the black hole spacetime metric. Okay. So in the first part, I will just briefly tell you a little bit about what we currently know, what we can do and know. And I'm excited to talk a little bit, especially with this audience, about what we think we can do in the future. What are the new observables that we can use? And what are the sorts of tests that we can hope to make? Okay, we also need numerical black hole spacetimes if we are to make statements about the fact that we can test these black holes. So what I mean is that if you have a simulation that's run in a Kerr black hole spacetime and you produce an image, you can compare this image to the image that EHT obtains and then say that, okay, there it matches or it doesn't match. But if you want to then say that you are testing a non-Kerr black hole against an image produced by the EHT, you should also equivalently have an image that is produced from some simulation in a non-Kerr spacetime, so that you can make a like-for-like comparison and as qualitative, as precise as possible. So for this reason, we now have to have simulations that sort of do that sort of study that characterize accretion in the non-Kerr spacetimes. And we have now recently constructed a library of such simulations. We have around 100. So in the first, I will just briefly show you qualitatively how there are differences between images of Kerr black holes as well as non-Kerr black holes, and try to say that there is hope for differentiating between them. And this also sort of is like a sanity check to what we currently say with the EHT, that we can actually tell the difference. Okay. Now, also generically, once you have a black hole that's going some accretion, that's undergoing some accretion, and the plasma is magnetized, bringing magnetic fields with it to the black hole, and the black hole is spinning, you generically get jets. So what we wanted to also see is when you look at the jets produced by non-Kerr black holes, do they follow roughly qualitatively the same physics as the jets that we see with Kerr black holes? In particular, what is the energy that, how is the energy generated in jets depending on the spacetime itself? So this is the sort of, this will be the last part of my talk here. Okay, so getting into the first one, I'll just restrict myself to spherically symmetric black holes because things are easy. But I'll make some comments about spinning black holes later on. So for any spherically symmetric black hole, you can write down the metric like this. It has 3 metric functions. You can actually remove one of them away by a coordinate transformation, but let's keep all of them, just to keep track of what things are entering in which observables.
So you're also saying stationary.
So this is, right. This is static and spherically symmetric. Yeah, right, absolutely. Because I'm thinking about the EHT kind of systems.
Maybe this is beyond, so like you could also have breathing. Right, where there's some periodicity, so on. So I mean, I guess my question is more, do people think about these things or, because I understand you have to start somewhere,
Right,
I'm just curious.
No, I think this is good. I honestly never thought of that.
I'm just thinking about the idea solution, for example.
Okay. So those are dynamically collapsing spacetimes, right? And so I guess what I would say is that over the timescales we're concerned about, I don't think the spacetime changes by much. So it's a good approximation station. Also, you can make arguments about the mass accretion rate and all of these things. It's like order 10, 8 orders of magnitude. So for that reason, I think it's reasonable to assume static. But maybe there might be a constraint if you use YDR, and can you say something else about what you can measure? Yeah, that's interesting. We can talk about that as well. So okay, here I'm thinking about spherically symmetric and static black holes. Thank you. And in particular, for the Schwarzschild metric, you have these metric functions. So in these spacetimes, solving for the photon orbits, which is a big part of the game, because what we're seeing the accretion because of photons that are carrying stuff, because the photons that are arriving at our screens. So solving for photon orbits is extremely simple in spherically symmetric spacetimes because they have 4 conserved quantities: the rest mass, which is 0, their energy at infinity, the azimuthal angular momentum, and the total angular. Now you might think that as soon as you have these 2 last conserved quantities, it's reminding you of the Kepler problem. Indeed, that's true. So in spherically symmetric spacetimes, all orbits are all planar. So they're actually moving on basically, in planes. They're not closed, but they're not always closed, but they're moving in planes. Okay. And in particular, you can define the impact parameter eta, which is the ratio of the total angular momentum and the energy. And this guy controls everything about the orbit. It is also the radius on the sky, on the image plane, at which this photon appears. Okay. So this is the guy that we'll need. And in particular, in black hole spacetimes, what you get is photons that are moving on circular orbits. This is the generic feature of black hole spacetimes. Once you have a horizon, you typically have, you always have photon spheres under some very minimal conditions, like the horizon is topologically spherical, all these sorts of very basic things. So this is a generic feature that you get photons moving on circular orbits. And you can solve for the radius of the photon orbit by just imposing that its radial velocity and the radial acceleration are 0. And setting these 2 conditions gives you also the impact parameter of the photon on that orbit. So what it's telling you is that you can solve this equation to get the radius of the photon orbit. You can solve this, you can use that in here to get the radius on the image plane of what is called the shadow of the black hole. Okay. And so the shadow is the gravitational lens size of the photon sphere. And for Schwarzschild, these are numbers that we get. And so let me tell you how the shadow turns up in actual EHT images. So let's say you have, so this is the black hole here. You have some disk that's emitting some material, some amount of photons, and it has some emissivity that falls off, like the rate of how many photons are emitting falls off in radius. That's some power law. And now you track photons that are going through this sort of disk, and you ask how much intensity would you get along this line of sight, along this particular photon orbit. Here on the right is the image plane. This is the impact parameter on the x-axis, which tells you how far you are from the center of the image plane. And this is telling you how much intensity you're picking up at each point. So these different photons are appearing at these different points. So you can see the photons that are that are just, that have large impact parameters. They are crossing a chunk of the disk, but the emissivity is small. So you get some small intensity on the image plane. Photons that are appearing much closer, they will intersect the disk twice, once on this side and once on this side. And they're appearing much closer. They're appearing somewhere here, and they'll have larger intensity on the image plane. In particular, photons that are orbiting infinite number of times, or close to infinite number of times, those are photons that are closer and closer to the photon, the circular photon orbit in the bulk. Therefore, they will appear close to the shadow boundary on the image planes. And you can see the spike here. That's where the shadow boundary is. And what this is qualitatively telling you is that the peak that you see in the intensity is very closely tied to the shadow boundary itself. So if you were to measure an image, if you were to see an image like we do with EHT, and you have a ring, then you can sort of infer what the shadow size itself is by doing some calibration, by comparing with images that you produced theoretically from theoretical simulation. So this is what we use currently with the EHT to sort of test gravity.
What sets the peak? Not the spike, the other peak, the number.
This one?
C. Yeah, it's something about the emissivity.
Yeah, absolutely. So this is a normalized intensity. It is going to be, yeah, it's there.
Why does it go down?
Why does it go down this way?
Between C and D. Why, if it was some power law or something between C and D, why the curve starts going down and then you get the spike?
Right. Here, if I remember correctly, the characteristic radius that they set is slightly outside the photon sphere. So what I mean is that the emissivity is peaking at some value and then falling off as a power law. So the radius at which it's peaking is what is between somewhere
So
between.
that's just an astrophysical assumption, maybe.
Right.
Yes.
Right.
C is n equals 1 here, right?
Sorry.
Yes.
C is an n equals 1, so it's being multiple events. The underlying power law is the much lower scale thing.
So the C is n equal to 0 itself.
No, C is n equals 1. You can see it from the vectors, right?
I thought that was
I don't know, C is still n equal to 0 because
C goes
I
through
mean,
the other
these set of
side.
photons, they are not.
Twice, and D goes through 3 times.
C is 3 times.
I think the astrophysical answer to your question is it's some combination of gas dynamics. So when you get close, you fall in quickly, and redshift. So
Yeah.
even if you had increasing emissivity all the way to the horizon, you get redshifted away, the spectrum is not going. So on. So if you were just to see the direct image, the n equals 0 image, it would not peak at the horizon boundary. It would peak slightly away from it, and so that's why you get a peak. It's not a power all the way in.
Yeah, you're right, Andrew. This one, it looks like it's going at least more than pi, and it's intersecting the disk also twice. So this would be the n equal to 1, like. Okay, thank you. Also, this figure sort of is telling you that.
Sorry, but then then C is there's a boundary between the ones that go only once and the ones that turn around and pass the.
Right.
You're saying that's not the spike. The spike is even the ones that. Why are there a bunch of peaks? The ones that go 1, 2, blah blah blah. They all get very close together exponentially or something at some rate. Is this what's going on?
Yeah, so this image we can think of as being a sum of different order images, 0, 1, 2, 3, etc. So so what we're seeing here is the sum of the 0th order image plus also the 1st order image, which is already sort of getting quite large. The 2nd order image is coming somewhere here, and all of them are stacking up somewhere in this sharp line because, like you're mentioning, they're becoming self-similarly close to the critical curve. So their intensity is stacking up somewhere here. But the intensity for the n equal to 1 is already coming here. So it's not very clear to say that, I can tell you where the difference between the n equal to 1 and n equal to 0 image boundaries is because they're stacking on top of each other. It's a combination of both, like George was mentioning, redshift, where the emissivity is peaking, how it matters for the n equal to 0, how it matters for the n equal to 1. All of that is sort of getting mixed up and turning up here. But what we can say is that this peak, generically, and you can do this for this inclination, for this black hole, for different, etc. This peak is going to be very close to the critical curve. That's what I want to use in this slide. Does that make sense? Okay.
So can you see a series of peaks if you zoom in?
Yeah, here you can.
Theoretically.
Yeah.
Up to optical depth.
Up to optical depth, of course. Yeah. Right. So, okay. So with all this, because we can actually actually, I'll skip this because let me show this. So with Sagittarius A, we actually quantified how far that peak that you saw, the emissivity maximum, the ring diameter like the ring diameter, how different is it from the shadow diameter? Let me say this again. So this peak or some peak that you see in the image, once you blur it, etc., how close is it to the theoretical value of the shadow boundary? So you can ask how this varies for different simulation for different images produced from different simulations, and that's what's shown on the x-axis here. So you can see that they are very close to zero. What this means is that the diameter of the ring appears very close to the shadow boundary generically over all simulations essentially. So this gives us some confidence and also some sense of how much the spread is in this particular relation to say that we can measure the shadow size. And with this, we can actually show that it's consistent, that Sagittarius A, for example, is consistent with a Kerr black hole, because the shadow size of a Kerr black hole and the shadow size of Sagittarius A match. We can also go once.
You know the shadow from, the mass in this case.
Right, yes, absolutely. Yeah,
So
exactly.
You know where
Right, exactly. So essentially, so then also we can go and look for non-Kerr black holes and ask if they have different hair, can we rule out some of these? And indeed, we can rule out some hair, and we can also rule out set constraints on some other hair. This is the sort of thing that we can do. So and we can also look at black holes that are coming from alternative theories. So all of this relies on the fact that we have this sort of characterization of the difference between the shadow size and the observed emission rings.
So the shadow diameter depends on the mass, the spin, as well as the deviation from Kerr.
Absolutely.
So you have to know the mass and the spin beforehand in order to pinpoint that, okay, this much is the deviation from Kerr.
So what we do is, so you don't, in GR, if you're looking at Kerr black holes, the deviation parameter depends only on the spin. But if you're looking at other black holes, the deviation parameter will depend on spin and all the other parameters. So you don't need the spin additionally to get the deviation parameter.
Okay.
So this is saying that there is a sort of 10% difference. There's a 10% difference between the two rates. But is this how I?
Right, exactly. Yeah.
So it's a 10% test of, assuming you know the mass perfectly, it's a 10%.
Absolutely. So we don't go to less than, I would say the width of the shadow diameter that we then produce from this is around 15 to 17%. So we don't get below this point. We're limited by it, exactly. Right. So this is the sort of process that we go through currently. In the future, we hope to be able to see these sharper features, which are these photon rings, because many in this audience have done some fundamental work in these directions. So what you see in a movie in a GRMHD movie of a Kerr black hole is this sharp ring here, which is this stacking of higher order images that are all overlapping, and this is a constant feature that you see. And you can see it also at different inclinations. You see the same guy turning up here, and that's what we call the photon ring. It is the sum of all higher order images of the entire accretion flow. Okay, so let me say a little bit about higher order images. We have talked already about it a little bit. Let's say this is a black hole. Sorry, this is an observer. This is a black hole.
So what do you mean by higher order?
That's exactly what I'm going to talk about here. Yeah. So, so let's say there's a blob of gas that's hot and emitting some photons. You will see one photon that will start from this location and end up here. So the total angular deflection that this photon undergoes is where it was, the difference between where it is observed and where it's emitted, the final condition minus the initial condition. I'm going to set my observer to be on the north pole, on the z-axis, positive z-axis, which is minus theta emission. Now there is also another photon that does this extra half loop. So this is the extra half loop, this bit, and it reaches the same observer. This is what I'm calling the first order image. And you can imagine that there's an infinite number of these, which are related whose angular deflections are related in this way. So what you can index them with this m which is the winding number, and this plus minus sign. And you can see that they go in this particular order. So the -0 guy is doing the least amount of deflection, the +1 guy is doing the next highest, etc. Instead of doing all this minus plus business, you can just index this set by n, and that's the order of the image. Okay, so this is what I mean by the order of the image. And this is for a small point source, let's say. For the entire accretion disk, it would just be a sum of the all order images of the entire accretion disk. So in particular, the photon ring that I was just talking about just previously is the sum of all higher order images, 1 and higher. Okay. So here is for a Schwarzschild black hole, these are a bunch of photons. They are all n equal to 0 photons. They start from just outside the horizon, 2m plus, and they're at different colatitudes. They're emitted from different theta, and they will all undergo different angular deflections and appear on the screen of the observer. And the distance from this vertical line here, that's the impact parameter of the photon. So you can see that the photons that are going larger angular deflections are appearing closer to the shadow boundary, which is this vertical line here, 3 rooms. These are the set of the first order photons from the same sources. What you can already see is that they're undergoing an extra half loop. So they're deflecting between pi and 2 pi. And also they're appearing on the opposite side of the screen. So opposite side of the screen. These will all in a Schwarzschild black hole spacetime appear on the same line on the screen. But they will do this sort of thing. And in this way, you can see that all higher order images you can write down, you can sort of write down in this way. And all even order images will appear on one side of the screen, all the odd order images will appear on the other side, exactly other side, in a spherically symmetric spacetime. Okay, and this is generically true for all order. So I just showed you for just outside the horizon, but you can do it for any radius, and you'll always get this. The important thing I want to emphasize here is that you can see that the image of this entire set of emitters is becoming increasingly smaller as you go to higher and higher orders. So you can think of the distance from the and they're also appearing increasingly closer to the shadow boundary here, as you can see. So you can ask how quickly they're approaching the shadow diameter, and they satisfy a relation of this kind. So let me just say what this means in a second. So this eta n plus 1 is the radius at which the n plus 1th image appears. Eta ps is the shadow size. This is telling you how close the n plus 1th image appears to the shadow boundary. Similarly for the nth image. So this distance decreases exponentially and is controlled by one parameter in spherically symmetric spacetimes called the Lensing-Lyapunov experiment. There's a single number which is determined purely by the spacetime. So there's this self-similar scaling symmetry. Okay, so what you can work out is that the angular deflection of photons that are appearing closer and closer and closer to the shadow boundary, they are undergoing larger and larger deflections. But in the bulk, they're looping around the photon sphere more and more times. In particular, this angular deflection is logarithmic. The divergence is logarithmic, and it's controlled by this exponent that I just introduced previously. And this eta bar is just the fractional distance. So it's the distance where the photon is appearing divided by the shadow diameter minus 1. So it's measuring how close you're appearing to the shadow size. So this is how this divergence goes. And you can also sort of work out the fact that different order images will undergo different levels of deflection. And if you use these two together, you will just end up with this sort of scaling relation. Okay, so because of the extra half loop that consecutive order photons are making, they appear at a later time because they're doing they have larger path lengths. And it turns out that this additional time delay is exactly given by pi times the shadow size. So if you were to measure the time delay between the first order photon and the 0th order photon, you would get an independent separate measurement of the shadow size.
It's just omega is the what?
Right. So that's I'm just trying to explain what that is. So we understand this by saying that okay, there's the difference between the first and the 0th photon is that the first photon is doing an additional half loop. That half loop that it's doing is basically moving on the photon sphere. So you can ask what is the angular velocity of a photon moving on the photon sphere. that is omega ps. And the time taken for it to do a half loop is just pi divided by the angular velocity. So that is where we're getting this number from. That's how we understand this answer. This is approximate, and I will show you why this is how good of an approximation this is. And so what this tells us is, at least in spherically symmetric spacetimes, you get another way to get the shadow size. We were doing calibration so far, but if we were able to measure this guy somehow, then we get another independent measure of the shadow size. And this is true also in the Kerr spacetime, that there's this particular relation. In general axisymmetric spacetimes, we have to still see. Okay. So there are these other, so let me just review what the spacetime critical parameters are. So you have this, we started off with this metric. We said that this is the photon sphere, this is the shadow size. These depend only on the metric functions f and r. They don't depend on the metric function g. This is something that was noted also in a paper in 2020 by Sagittarius et al. So what this means is, if you measure the shadow size, this guy, you get a measurement effectively of this metric function f of gt. You are accessing a certain portion of the metric. Now it turns out that this Lensing-Lyapunov exponent that I introduced, you can write it in terms of this other exponent I will talk about in a second. And it depends in general on all three metric functions, as you can see here. It depends also on this g. So if you are able to measure this Lensing-Lyapunov exponent by looking at the demagnification of images, then you get access to some new information about the spacetime. And this we will see why it can be not trivial. Okay, so I introduced this new parameter called the phase space Lyapunov exponent. Let me explain it like this. So here I have radius on the x-axis, and on the y-axis, the affine parameter along the photon. Let me take one photon, the orange guy, that is going on a circular orbit. That's just looping around, staying at the same radius at all affine times. Now let me take the blue guy. It's starting off slightly outside the photon sphere. So this guy's orbit, determined by the instability at the photon sphere, will just be that it will diverge, it will deflect away from the photon sphere exponentially quickly. And the rate of this divergence is given by this exponent called the Lyapunov exponent. So this is a phase space picture. That's why I call it a phase space Lyapunov exponent. Okay. So this phase space Lyapunov exponent, this is telling you how quickly photon orbits diverge close to the photon sphere, is what is setting also this Lyapunov exponent, the Lensing-Lyapunov exponent.
So these, I assume, have all definitions that are like gauge invariant and things like this, because if you write like this, I don't know.
This one is not. So this is the guy that's gauge invariant. So I can introduce the Lyapunov time, where I've changed now from the affine parameter to the asymptotic observer's time. Therefore, it's gauge invariant. And now you can ask how quickly do these two orbits diverge by a factor of the Euler number, that is then the Lyapunov time. This is a gauge invariant quantity. Okay, so this quantity also depends on this phase space Lyapunov exponent. And this phase space Lyapunov exponent is also important when you're thinking about stability of black holes, because it sort of sets the decay rates and things like that. Okay. Good. So one more thing I want to note is that the ratio of the time delay and the Lyapunov time is also the Lensing-Lyapunov exponent. So what this means is that if you were to measure the top guy and the bottom guy some way, then you would also get an independent measurement of the Lyapunov exponent, the Lensing-Lyapunov exponent.
If you're still in n equals 0, n equals 1, is that ratio hold?
No, it's
certainly the individual ones don't hold, but.
So firstly, when it's, these are all higher order in formula. There's also corrections if you go off the equatorial plane, even for higher order formula, right? So this is just a character. If you define the different constants, the fundamental constants in this way, this TL is this T, the time delay is a characteristic time, then this holds. So what I mean is this. Yeah, right. Okay. Cool. So I'll just tell you on the next slide why this is approximate. Finally, I will just say that the Kurzweil mode frequencies are also related to all these guys that have appeared here already in spherically symmetric spacetimes. In particular, the real part is 1 over the shadow size, and the imaginary part, which is the damping time, is also the Lyapunov time. So we see in this way that all these are sort of related quite nicely. Okay. This is for spherically symmetric black holes.
But general or just Schwarz?
No, this is fully general. Any spherically symmetric spacetime. Yeah, and these are the numbers that you get for Schwarzschild. So in particular, the Lyapunov time is this root 27n. That how would be nice to measure. Okay, so one thing that we can do to try to measure the time delay is observe flaring events. So these are events where the compact flux, so the flux sort of increases sharply, and these are also sort of compact flux sources that appear on the image plane. So we model them as hotspots in various works. And so the way that we can think about it is that this guy here is the n equal to 0 image of the hotspot that's gone off in the bulk. And this guy is the n equal to 1 image of the hotspot that's appeared. And okay, let me actually play this movie. So you can see here, the hotspot has already gone off in the bulk. It'll appear after some time on the image plane because of the travel time from the hotspot to the image plane, right? And the hotspot is moving. The n equal to 0 image will appear somewhere here because it has taken some extra time. It has emitted at the same time at t equal to 0. It has taken some extra time and it appears
Equals to 1.
n equal to 1, right? And then they both move together. So the hotspot in the bulk is going around in a circular orbit. And here you see that they both turn up and then they move around together. So what we're talking about is the time delay between the appearance of these two guys, whether we can actually get for the n equal to 0 and n equal to 1 to be quite nicely pi times the shadow size. Okay, so here is, maybe I'll skip this because of time. Okay, so here I compute in the top the time delay, exact time delay between the first order image appearing and the 0th order image appearing when the hotspot is at some angle, some inclination, and at some different radius. And I divide that by the delay time, the characteristic delay time that we want to go after, because this is the error that will tell you whether you can get the shadow size or not. And you can see that you get large errors in general.
I want to make sure I understand your plot.
Yeah.
The x-axis is in units of pi.
Yeah, right. Absolutely. Exactly. And on the right here, we have accounted for the inclination of the hotspot. There's a formula that from the scaling relations directly you can get. And if you account for this sort of inclination of the hotspot.
What do you mean inclination of the heart?
So
In the
you are,
orbit.
no. So here at the hotspot, let's say it goes up at one point, right? Where is it located in space? So let's say you're on the z-axis. Then is the hotspot, what whole latitude is the hotspot at? And at what radius from the black hole is it? So those are the two points. So because if the hotspot is closer to you, then the n equal to 0 image will take a shorter length, the n equal to 1 will take a longer length. So there'll be an effect because of that. Right. So that's what this formula is accounting for. And so if you do that, you can cancel out, these isocontives look parallel essentially to the radius. And we also understand the radial dependence. So if you try to account for that as well, you can get the errors even further and further down. And these are just coming from geometry and lensing. So this is not about the astrophysics yet. There will be those complications, but we just wanted to see whether you can get down the errors for realistic locations of the hotspot and see if there's a hope to even get the shadow size. So this is work in progress, but this looks a little promising. Okay. We saw for point sources that this thing holds. The same thing should hold for the diameters of higher order images that you see here, diameters, widths, etc. So that's how it would work for extended sources. And in particular, like I said, the widths also scale in the same way. The fluxes that you see in those rings also scale the same way, etc. So the Lyapunov time now, I have very little time left, so I'll go a little quickly. So here is an experiment thought experiment where you have a star falling into a black hole, like it's radially falling into a black hole, and this is a light curve of this event that was worked out in this paper. And there's also an earlier paper by Ames and Lee. So what they see in this normalized light curve is that you have the fluxes doing this, and then at late times, generically, it falls off exponentially. And this exponential fall off is basically the Lyapunov time. And the way to understand this is that the star is falling towards the black hole, is shooting a bunch of photons isotropically at every point. Some of them making it to us. Some of the photons are going towards the black hole. They are starting to loop around, and the star falls into the black hole. And some of the photons that were looping around from previous times, they are sort of being emitted. And the rate at which they're being emitted is basically the instability timescale of photons at the photon shell. So that's one way to potentially get the Lyapunov time. of course, I don't know how many stars we're going to see falling in. But more seriously, there's this work which sort of tries to apply this, I mean, in some way to a gas cloud falling into Sagittarius. Maybe if you look at the light curve there with enough flux sensitivity, maybe we'll be able to see this. It's also unclear whether we can see this from hotspots in any way. So these are things that we could investigate.
So what's the time there, when did why 100, what's this about the 10?
So I think in this case, I don't remember exactly, but I think they're setting the observer to lie around at 100 distance or so. I have to check again how the time scale is set. Or maybe, yeah, I will get back in. Yeah. Okay, so with all this, with these different parameters that we talked about, the shadow size, the Lyapunov time, and the Lyapunov Lyapunov exponent, these three guys, what can we do with tests of gravity? So these three different deviation parameters are telling you how different they're from the Schwarzschild value. And here are four different black hole parameter spaces. So you can see that, so the red lines are isocontours of the Lyapunov exponent, the scaling guy. The blue lines are the shadow size, and the green guys are the Lyapunov time. So if you get a joint measurement of any pair of these, then you will be able to establish much stronger tests than we currently can. So in particular, you can see that this hatch region, which is not very clear to see, these are the shadow bounds that we get already with EHT. And these actually extend. So if you look at this plot here, these actually extend in this direction to infinity, as well as in this direction to infinity. So if you get an additional measurement of one of these other exponents, you get orthogonal isocontours, and you make that region compact. So this would be a precision test of GR. And in the bottom right here, I'm showing you how like this is a parameter space that we can't access with EHT at all, because all of these black holes here are the same shadow size. And these are differing in the G metric function that I showed earlier. So this is something that we can also do with a new measurement of one of these other critical exponents. Finally, here, what we wanted to show was that the first order image width can also give you something about the space-time geometry. So what we do is that we use a simple analytic model for the disk morphology, a thick disk. And we ask what is the width of the first higher order image of this emitting region in different black hole spacetimes. And we look at the widths, and the widths have these different isocontours. And again, here, the shadow size isocontours that I showed you previously are going like this. So measuring the width of the first order ring can also give you some level of constraints, because those isocontours are orthogonal to the shadow size isocontours, which would be the diameter of the inequivalent ring.
How sensitive is this to the pi over 10?
I don't, it's really not. So I chose this pi over 10 because, so this is around 0.3. And in this paper by like Ramesh and Andrew, they get HOR of 0.4 or so, which translates to a sort of scale height of 0.2. So I just chose a 0.3 so that it's slightly even thicker. Does that change things? And for that, I get these isocontours. So if I change this pi over 10 to whatever, some other value, it would be different. But the qualitative thing would be that you would still get widths that are orthogonal to the diameters.
Because you could, in principle, you could measure the R in and the R out in
Yeah.
n equals 0.
Yeah,
And then so you can, but you can't measure the
Right.
beta 1/2.
yeah, exactly. Right. Okay, so I should now switch. I will talk about, in the last 10 minutes that I have, very quickly. I'll just talk about the simulation. This will be brief, the images and the jets. So here is the slide that I was going to talk about with Kerr. So this is the same. This metric looks basically like Kerr. So it has the same metric functions, same structure, etc. But now you can relax these metric functions to be some other kinds of metric functions, and therefore describe other kinds of black holes. If you do this, you can really put this metric into a form that is suitable for GRMHT code. So you have four metric functions that you have to prescribe from your favorite black hole spacetime. You input this guy into your GRMHT code, you can do simulations. And this is what we sort of used to do the first numerical simulations in spinning non-Kerr black hole spacetimes. So the first guy that we used was this guy from string theory. It's called the Kerr-Stein metric. It has this form again, and it differs from the Kerr metric in this way. This D is the dilaton charge, or the axion charge, or the electromagnetic field charge. It depends on all these three things, and the spacetime has all, or this black hole has all these three. So in the first set of simulations, we looked at these dilaton black hole, these dilaton axion black holes. So in the top is non-spinning black holes. In the bottom are spinning black holes of the same spin, 0.5. These are the Kerr black holes, and these are these string theory black holes. So what you see is you can already see that the black hole sizes are becoming like quite different as you go crossover from Kerr to non-Kerr. And this is something this is a handle that we get by looking at these different spacetimes.
But what do you mean by this string theory?
Ah.
What mass is it? Because I thought, what is this?
Yeah. So we start off from. So one can start off from this type 2B string theory in 11 dimensions. You have whatever. You can come heterotic string, and you can compactify and look at the low energy effective limit. And this limit has an action that I can write down. It has the gravitational sector is still Einstein-Hilbert, and then you have an additional scalar field which is called the dilaton, and you have an additional axionic field, and you have kinetic terms for those, and you also have a Maxwell field. So these are the different fields that are coming in this low energy effective limit. So from that, what we do is that we look at the stationary solutions of that theory, and you get Kerr.
But the properties of this dilaton, for example, you have to be curved and stabilized. I don't know.
Yeah.
But it has some kind of bad consequences and all kind of other things. Are you consistent with?
Yes. So these dilatons are not problematic as far as I know. There are other kinds of dilaton models with different potentials, etc., different couplings. These, as far as I understand, are fine. And so yeah, right. So and you also have solutions for the dilaton and the axion and so. Yeah. Okay. So here are 4 different simulations, and here are snapshots from these simulations. You can see that this black hole, the absolute smallest black hole that you can get in this entire game with this class of metrics, that looks pretty small. And this is already you can already rule this out from EHT measurements. You can also see in this case the black hole size is getting a little smaller, but it's still not comparably small. You can't just rule it out immediately. You'll have to do some more work.
Why do you make it smaller?
No, we're just exploring the parameter space of this.
Yeah, but why? Like, why does this value of the smaller size of?
So the way to think about it is that typically when you have an additional charge, you have an additional field. What is happening is that there is some energy density that you're storing in the field, and these fields, they go from r equal to 0 to infinity. So in particular, outside the horizon, you are storing energy in the fields. When you fix the black hole mass and change the charge, the black hole is getting smaller because you're storing more energy in the field outside.
So effectively, its mass is becoming smaller, so the eventual horizon shrink.
The mass of the black hole is getting
Mass of
smaller.
the black hole is
The Hawking mass of the horizon getting smaller. Yeah, absolutely. I should speed up. Okay, so here is a reconstruction for the 2 cases that with future arrays, NGHT in particular. So these are the 2 cases that had the same spin and were not very easy to distinguish. But if you look at the brightness temperature as a function of the impact parameter essentially on the sky, you see these 2 curves. The top one belongs to Kerr, and the top one belongs to the string theory black hole, and the bottom one belongs to Kerr. They sort of separate out. So the contrast in the inner shadow region is what is also turns out to be an observable in this case, which would distinguish different kinds of black holes. So there's some hope. So finally, we also look at these other parameterized metrics. These parameterized metrics are not solutions to any particular theory, but what they allow us to do is they provide handles, parameters that you can tune so that you can change different kinds of physics. So for example, this parameter alpha 13, for a black hole of the same mass and spin, alpha 13 makes the shadow more circular as well as it changes the size of the shadow. And this parameter alpha 22, for the same mass and spin of the black hole, it adds more quadrupole moment, which means, or it reduces, which means you have more frame dragging or lesser frame dragging than the Kerr counterpart. So what you can see, there are 4 sets of panels here. In the top, this set, in the top is the 86 gigahertz image, which shows jets at much larger scales. And the dynamic range here we've chosen as 10,000. In the bottom left is the image at 230 gigahertz for M87 inclination. So this is all M87 here, 163 degrees. And this is the same image of the same black hole, but when viewed from the equatorial plane. So we have these set of figures for the different kinds of black holes. Here is a Kerr black hole. You see a more powerful jet because the black hole is spinning. Here is a black hole with this different alpha 1,3 parameter. And you can see that the black hole shadow is larger than in the Kerr case. And it has a weaker jet as well. Finally, with this, for this case, when you add this extra quadrupole moment, you get a much stronger jet than even in the Kerr case. And you can also see the asymmetry in the shadow because of stronger frame driving. So these are things that we can hope to sort of also see in the future. So let me, in the last few minutes that I have, tell you a little bit about the jet power in the last 5 minutes. So, okay. When you have a disk that is sort of bringing magnetic fields close to you, close to the black hole, here are the magnetic fields in this high quality picture. Here's the disk, which is magnetized. And it's bringing a bunch of magnetic fields to the black hole, and the magnetic fields are being spun up by the black hole itself. So these are imagined to be having toroidal loops, but I'm not drawing that. In this region, you will have magnetically dominated plasma that's outflowing out in the outward direction. And this is what we're referring to as jet. So what I'm interested in here is the power that you can get from this jet and how this is set by the black hole itself, right? So, okay, I'm going to now step back and think about this, thanks to Sasha Chekhov's as a tube with some energy flux. So there's a tube here, and there is some energy flowing through the tube. You can compute the power through the tube by multiplying the energy density of the material times the cross-section area times the velocity of the material that's flowing through. So since this is magnetically dominated, the energy density is given by the magnetic field. So it goes as b squared. It should go as b squared over 8 pi, but I'm ignoring those factors. So this is the energy density. This is the area of the cross-section area, and everything is moving at the speed of c. So this gives you a rough measure of the power. This is how it's going. And is also modulated by the spin, because what you find is that larger spin black holes are going to produce more powerful jets, and lower, zero spin black holes are going to produce almost zero jets. So this is roughly the way that we understand the structure of this formula. We can rewrite this in this very nice way. We can introduce the horizon magnetic flux, which is the magnetic field times the area, and rewrite this in this way to see that this quantity here depends only on the black hole. The spin of the black hole, the mass of the black hole. Rg is the gravitational radius of the black hole. And this phi depends on how much magnetic flux that you've put on the horizon. So you've separated it into a thing that is purely the black hole spacetime, and you're into something that depends on the state of accretion theory. And it was found in some work that this formula should actually be corrected to phi squared omega h squared, where omega h is the angular velocity of the horizon. In the limit a goes to 0, you get back this result. So, using some very nice simulations, they were able to show that it should go this way. So I'm running out of time, so I will just sort of flash this really quickly. So you can ask, what is the maximum jet power that you can get using this formula? And that will correspond to some maximum magnetic flux that you can pack onto the horizon. So this is the maximum jet power that you get. You can ask, what is the efficiency of the jet, which is the power that you're extracting from it divided by the energy flux that is flowing into the black hole. So this plasma. If this quantity is greater than 1, then what you find is that you're getting more power out of the system than you put through accretion. And therefore, this power must be coming from somewhere. It's coming from the black hole. You're spinning down the black hole, extracting energy from its ergo region, and you're generating these outflows via an electromagnetic Penrose process. So what we wanted to check with these set of simulations is, this is my final slide, is how, if you take a bunch of Kerr black holes and non-Kerr black holes, is the energy, is the jet efficiency, which is the energy divided, the power divided by the accretion rate, as I described earlier, is this following the same physics? It doesn't depend on the space-time at all. So here on the x-axis is the magnetic flux on the horizon at its saturated value that we obtain from these simulations, multiplied by this the horizon angular velocity of this black hole, which you get from the black hole spacetime itself. And this is the efficiency, and it follows this beautiful quadratic relation in with respect to these parameters. And these are all the these are around 39 black holes, which are also in like many of 10 are Kerr black holes, and the rest are in string theory black holes. Here are another 60 odd simulations in these parameterized metrics. What you see is that all of these black holes follow precisely the same curve. It doesn't really depend on the metric in particular. So they follow some beautiful physics that depends only on these two parameters. It doesn't depend on the details of the spacetime. Of course, the spacetime itself influences this phi h, because as this plot sort of tells you that if you change the spacetime and divide it, so you see that there are different trends for different spacetimes. So with this, I'll just end. Sorry for running over time. So what we found is that there are a number of critical parameters that you get in spherically symmetric spacetimes and axisymmetric spacetimes that control different images. And these are this delay time, this Lensing-Lyapunov exponent, and the Lyapunov time. And we can probably measure some of these and infer more information about the spacetime geometry and set up more newer tests. Also, we find that the n equal to 1 ring width might also impose some non-trivial constraints on black hole parameter spaces. So if we could measure this or an upper bound on this, that could also be quite interesting. So finally, the simulations in these non-Kerr spacetimes are becoming possible, and we use these to show that that you can actually distinguish between the images of black holes, and also we studied the energetics of the jets produced by these black holes, and they display this beautiful, simple, universal behavior depending only on the magnetic flux at the horizon and the angular velocity of the black hole. So this is quite interesting, and it opens up some nice questions. How do you understand the relation between the spacetime and the magnetic flux on the horizon? How much magnetic flux can you pack onto it? So these are things that we're thinking about, and I'll leave you with that. Thank you for your attention.
Okay, so we've gone slightly over time, but maybe if there's like one or two burning questions. Andrew.
In the plot where you plot P jet versus omega phi, is the underlying line there just parabola, or do you have to consider higher order corrections as well?
Okay. So we actually looked at higher order corrections, and because in the Narayan et al. Paper, Tchaikovsky et al. Paper, if you consider higher order corrections, this actually goes down like this, because the term in the omega 4 is negative. And we try to do that. And so in particular, if you look here, the maximum Kerr jet power is here, jet efficiency is here. And if you go further, these actually curves diverge. So this was one, this is one thing that we find, that actually the leading order term is sufficient, which we found very interesting.
Sorry, I'm like just confused. Like, why would you want to make a curve where all of these things lie on the same thing? Like, you should differentiate them as much as you want, like in the parameter. I mean, why do you want a universality thing?
No. So this is this part is not about trying. Okay. So this is about trying to understand what is setting the jet power itself, right? Is it? There must be some details that depend on the spacetime, and that is coming in through the magnetic flux itself, this phi h. So they do differ, but not at this level, but at the more slightly granular level, I guess, of the horizon magnetic flux itself. Yeah.
I thought like approach would be like to use observations to distinguish between these different scenarios.
You sort of maybe can as well, because maybe with some spectral indices at different frequencies, you can get the mass accretion rate somehow probably. And then you try to use that and use 86 gigahertz jet power to then say that, okay, there is some band on the y-axis, right? So you could do something like that and just say that I can tell different black holes apart in that way. I don't know what the uncertainties of this. It's just we have to think about that. So.
Okay, did you?
Yeah, just before when you were talking about measuring these time delays.
Sorry?
Before when you were talking about measuring these like time delays.
Right, yeah.
I was just curious because you needed to have some kind of flare. It needs to be, brighter than the rest of the
Yeah,
accretion disk by some
absolutely.
amount. Presumably it has some like scale, some physical scale. How do
Yeah.
these translate into errors on these parameters and like how much resolution do you need to measure things
Absolutely.
like?
So typically, I think from work done by Riperda and others, I think the scale of these, the physical scale of these hotspots around 1 gravitational radius. Roughly. Does that make sense?
That is a consistent number.
Okay. Okay, so there are caveats clearly. But roughly that is the scale. So yeah, so in these so here I should say this stuff is all, I'm assuming it is point particle and trying to see what's going on. But we are actually doing the same, we're following up with actual movies of hotspots. So the way we model these, we still don't take the background disk into account. So we're just saying one guy has turned up. It is described by a Gaussian number density of electrons. It has a magnetic field prescription. And then we compute everything using slow light. And we're trying to see if we can get the time delay precisely or roughly to match what we're getting from our point source stuff. This is the first step in that direction. We don't know the answer to the uncertainties involved. In the future, we'll have to actually turn on. So this is a coherent spot that's going around on an orbit. We'll have to turn on effects like shearing, which will actually destroy this hotspot on some time scale. We'll also have to incorporate the background accretion disk as well. These are steps that we'll work out soon. But at least I don't have a sense of how well we can actually do this. I will say one last thing. From reconstructions of this, people think that with future arrays you can actually get movies like this if the source looks like this. You can actually reconstruct these higher order images. So yeah, but we have to still take into account the background.
And I think we should end at this point, but Prashant will be around this afternoon and also tomorrow. We're all going to go to lunch now, so you can continue the conversation there. Also, I think there are like 2 spots left for dinner, so if you want to sign up for that this evening, we are probably going to A to B. Even the proponents of vegetarians will be going. And so anyway, let's thank Prashant. Thank you.